Okay, so we have seen these two subspace methods. They are called subspace method because they rely on particular algebraic properties of the correlation matrix of the data. And in particular, once you have derived the eigenvector, eigenvalue decomposition of the correlation matrix, you separate the eigenvector associated to the noise only, and they generate what is called noise subspace. And then on the other side, you have the eigenvectors associated to the signal eigenvalues plus noise eigenvalues. Actually, it should be signal plus noise subspace, but briefly speaking, the subspace where the signal is confined, even if it contains also noise, it is called signal subspace. So the eigenvector, eigenvalue decomposition of the correlation matrix allows to find two orthonormal bases, one for the noise subspace, the other for the signal subspace, and they are orthogonal. And it is exactly this orthogonality that allows to find the directional arrival of the K source present in the data, basically by calculating this product between the array response calculated in generic angle theta that multiplies the estimated orthonormal base for the noise subspace. So music uses the noise subspace, not the signal subspace. And all the times that theta is equal to one of the K directional arrival of the sources, this quantity ideally should be zero. So the reciprocal should be infinite. Obviously, because we don't know G, we should estimate from the data. So we estimate G by calculating the eigenvector, eigenvalue decomposition of the sample covariance matrix. It will not be zero, but we hope if the estimate is not too bad, this quantity is small, so the reciprocal have a peak. So to estimate the directional arrival by using spectral music, basically we should build this pseudospectrum, this is called music pseudospectrum, and make a search with respect to the single parameter theta of the K largest peak. Now, if the array is Euler, we have seen that the relationship between the vector A and the steering direction theta becomes the one reported in this expression. So it's non-linear, but if the array Euler is this is the expression of the array response. And if you make this replacement, if in place of e to j to pi fs, where fs is the normalized partial frequency, the problem of finding the value of theta for which this quantity is zero, with this replacement, in the case the array is Euler, this becomes a polynomial. And so the problem in this particular case can be transformed in the problem of finding the roots of this polynomial. Once you have the roots, you can find an estimate of the directional arrival. So only in the case where the array is Euler, the nonlinear maximization problem with respect to parameter theta can be reverted into a problem of finding the roots of the polynomial. And based on the property of this polynomial, we understood that we are interested on the K roots closest to the unit circle. These roots defines the signal subspace. The other roots are the noise roots. And we made some comment to explain why spectral music is affected by an error both in the amplitude and in the phase. And instead, root music, or the way it works, it is affected only by an error in the phase, not by an error in the modulo of the root. And so this is the reason why, as you will see later, root music has better performance, than spectral music. Okay, let's see some numerical results. And you have all the MATLAB code. I send you all the MATLAB code also for this chapter. So the assumptions are the usual. In particular, we model the signal. So the K signal generated by the source as wide Gaussian processes. So the signal are temporally wide and Gaussian. The spatial correlation is RS, which is obviously not the identity matrix. As concerning the noise is spatially and temporally wide and Gaussian. Obviously, in the simulation, you can change these things. You can introduce a color in the noise. I mean, you can do a number of changes. So let's assume first that the array is EULA, so we can use both spectral music and root music. We have three sources with direction arrival -10 degrees, 0 degrees, 60 degrees. The covariance matrix is this of the signal is this one, the spatial covariance matrix. The powers of the three sources are different, 1/10, 1/4. And then all the off-diagonal elements are 0. The fact that they are 0 means that the sources are uncorrelated. And because we assume that they are Gaussian, you know that if a vector is Gaussian, uncorrelation implies independence. Independence always implies uncorrelation, but the reverse is true only for Gaussian processes, for Gaussian random vectors. So in the first numerical example, we assume that there is no noise, and in the other example, we assume that there is noise with power 1. Now, in the case where there is no noise, obviously the true data covariance matrix is equal to the signal covariance matrix. So it is rank deficient because it's a 15 by 15 matrix with rank 3. So it cannot be inverted. To be able to invert it, we introduce the diagonal loading. So we introduce the diagonal loading only in the case where the noise power is 0. And diagonal loading with loading factor 0.2. So this is what we derive in this case. So you see the classical beamforming, the green curve. So it has the poorest resolution because the three peaks are wider, and then it has side lobes. Then you can see Capon. Capon has three peaks, much narrower than the classical beamformer. So Capon, so remember, the classical beamformer is non-adaptive, non-parametric. Introducing adaptivity by optimizing some performance criteria, as you have seen, we achieve better resolution. And if you use a model-based approach, for example, music, we achieve even better resolution than Capon. So that's why music belongs to the category of super resolution methods. And as I said, the information in the music pseudospectrum is not in the shape of the spectrum, but only in the position of the three peaks. And you see three peaks at the right angles. Now, if there is noise, we don't need diagonal loading. Obviously, we can introduce diagonal loading for the reason that I explained. And I repeat, in practice, in most of the system, some level of diagonal loading is always present because it makes the beamformer more robust to non-idealities. Okay, so in the presence of noise, this is what we get. And I have scaled the estimate in order that the maximum is 1 for all of them. So if you plot in dB, the maximum is 0 dB for all of them. But this is because I scale in order to plot them in the same figure, okay? And again, what you can see is that the classical beamformer has the worst resolution. Capon has resolution that is intermediate between the super resolution method music and the classical beamformer. If the sources are closer, so here the difference is 10 degrees between theta 1 and theta 2. If the sources are closer, so for example, theta 1 is minus 7 degrees, obviously it's more difficult to separate them. And you can see that with this setting, with this level of noise, notice that the power of the noise is 1. The power of the first source is 1/10, so 10 times smaller. The power of the second source is 1, so it's equal to the power of the noise. And the power of the third source is 1/4, so 4 times smaller than the noise power. So what we observe is that with these values of the parameters, the two close sources are no more separated, neither by the classical beamformer nor by the Capon beamformer. Also, Capon has problems in resolving them. Still, the music pseudospectrum allows you to see a clear peak separated from the main peak. And so you can estimate pretty correctly the three values. In this case, okay, here the number of snapshots is 128. Remember, the resolution of the classical beamformer and Capon does not improve with the number of snapshots because it depends mostly on the number of sensors. On the reverse, music is consistent with respect to the number of snapshots. So if you increase n, so for example, if you double n, you don't see a significant difference in the classical and Capon estimate of the power spectral density. but you notice an improvement in music because this peak is more pronounced. This is due to the fact that music is a consistent estimator, and the estimate tends to be perfect when n goes to infinity. So you don't need m to go to infinity. So this is very important. If you calculate the estimate of the three-directional arrival by using root music, and we can do because in this example, the array is Euler, you can see that in the absence of noise, the estimate is perfect. In the two other cases, still, obviously, we have an error in the estimate, but the sources can be separated. Here, the order is different. So we have one estimate that is close to 60 degrees, one that is close to 0, and one that is close to -7. And so we are able to separate the source at -7 from the source at 0 dB. If n increases, the accuracy is even better. So the error in the estimate is smaller. This is closer to 0, as you can see. But what is important to notice here is that both spectral music and the root music are able to resolve the two closed sources even when the classical beamformer and Capon are not able to separate these two sources. So the resolution of music is better both than the classical beamformer and also better than Capon. So that's why it belongs to the class of so-called super resolution methods. There are many others, and I repeat, we don't have time to enter in the detail of all these methods. But there is a problem, as I told you, when some sources are correlated. So for example, if we assume that source 1 and source 3 are correlated, so in position 1, 3, you have the cross correlation. So this term here basically is what? Is the product, so the element of position 1, 3 is the product between the correlation coefficient rho times the square root of the power. Now, because the power in this case of both the source 1 and 3 is 1, here you have the correlation coefficient, which is assumed to be 0.99. So if source 1 and 3 are highly correlated with correlation coefficient 0.99, this is the shape of matrix RS. Clearly, the second source is uncorrelated with the other two. Now, if you compare what happens, uncorrelated, correlated. When two of the sources are correlated, both Capon and music breaks down, doesn't work well. Instead, the classical beamformer is more robust. It does not need an estimate of the data covariance matrix. Remember, Capon and music require an estimate of the data covariance matrix. Then they use this estimate in a different manner, but they use. The classical beamformer does not require, it is just a matched filter. So the structure of the classical beamformer just depends on the array response. So it's enough that the array is calibrated. You don't need to estimate the data covariance matrix. And so either you use the classical beamformer Or, as I said, there are more sophisticated versions of music that in some way cure this problem, uh, obviously at the cost of additional computational complexity. This method, I repeat, I will not enter into details, but if you are curious, you can check for the spatial smoothing version of music. It is one, and the other is the so-called forward-backward spatial smoothing version of music. These two different methods basically address the problem that in the presence of coherent sources, so highly correlated sources or completely correlated sources, the rank of the correlation matrix Rs is no more equal to the number of sources, but is smaller. And this creates the problem that you have seen. Clearly, because the last m minus k eigenvalues ideally should be equal to the noise power, you can get an estimate of the noise power by calculating the arithmetic mean of the smallest m minus k eigenvalues. So you can estimate both the directional arrival of the k sources and the power of the noise from the eigenvalues. So remember, there were three categories. We have seen spectral music and root music that belongs each one to the first two categories. The most important method that belongs to the third category of subspace method is called Esprit. Esprit is probably the most widely adopted subspace method. Esprit of variants of Esprit. So Esprit was proposed by Professor Thomas Kailat, and it's the acronym of estimation of signal parameters via rotational invariance technique. And it has a number of advantages over music that I will try to highlight. So let's introduce Esprit. Esprit, exactly like music, can be used not only to estimate the directional arrival of sources, but it can be used also to estimate the frequencies of multi-component cosinusoidal signal. Esprit has been derived under the assumption that the signal is point light as music, and it can be applied not to any array geometry, but it does not require the array to be EULA like root music. So it can be applied to a general class of arrays that have a particular property that I will introduce now. Actually, Esprit can be used also to estimate the parameters of damped sinusoid. So I mean, the applicability of Esprit is larger than music in general. But let's go to the description of music. Sorry, the description of Esprit. So basically, Esprit, the Esprit method can be organized in three steps. In the first step, we estimate the signal subspace, and this is the first difference with respect to music. Music uses the noise subspace. Esprit uses the signal subspace. Then we built and we solved an overdetermined system of equation. These equations are called invariance equation. And once we have solved this invariance equation, we calculate the estimate that we are looking for. Esprit can be generalized to the r-dimensional case, two-dimensional, and so on, but I will not enter in this detail here. Okay, so let's try to understand how Esprit works. The first important assumption is that the array can be any, so it does not need to be Euler, but what is fundamental is that it has this property. It can be organized or separated into identical subarrays. So two identical subarrays that are spaced. So the second subarray can be thought of obtained from a translation of the first subarray, a rigid translation without rotation. So the vector D is the vector that tells you what is the distance between two elements in the two subarrays in the similar position. So D is the difference vector between these two, but it is also the difference vector between this and this, but also the difference vector between this and this, and so on. So we have an array made by M sensors, and this array should have this particular property that can be organized into different subarrays, each one composed by, let's say, M over bar sensors. And I mean, there can be an overlap between the two in the sense that in this figure, it does not happen. In this figure, M over bar is M divided by 2. But it is not necessary that there is no overlap between the two subarrays. And actually, if the array is Euler, we consider the subarray with maximum overlap. I will show you in a second. So the steering matrix of subarray 1 can be thought as obtained from the steering matrix of the whole array by setting some elements at 0. So this matrix here allows you to select M over bar elements from the whole array to form the first subarray. And in a similar manner, we select the M over bar elements of the second subarray. Now, as I said, we don't need to choose M over bar half of the number of sensor M. For example, if you have an array Euler, so made by M elements, we can choose the two subarray in order to have the maximum overlap. And this is the choice, the typical choice that we do in the case of array Euler. So the first subarray is composed by the first M-1 elements. The second subarray is composed by the last M-1 elements. So in this case, M over bar is M-1. And these elements from the second to the M-1 belongs to both subarray. So you don't have constraint on this. What is important is that given the array, it's possible to organize to split the whole array into identical subarray, maybe with some overlap. Now, what is the relationship between the two steering matrices? I mean, the delay between this sensor and this sensor is the same as the delay between this sensor and this sensor. And is the same as the delay between this sensor and this sensor. And how is derived this delay? Is derived by calculating the inner product between the vector pointing into the direction of propagation and d. So if you calculate the component of d, so the displacement vector, along this direction, and you divide by the speed of propagation, you find the delay between equivalent elements in the two subarrays. So if there is only one source, the relationship between this and this is just a multiplication of a phase term. So you can multiply by a scalar because the delay is the same for each couple of elements in the array 2, subarray 2, subarray 1. Obviously, if you have k targets, they come from k different direction arrival. So you have k different delays. So in that case, this relationship is expressed by this matrix D, which is a diagonal k by k matrix. Now, if this matrix is diagonal, obviously the elements on the diagonal are also the eigenvalues. So given the geometry of the array, we have the relationship between the direction arrival and the delay we have seen at the beginning of the course. For example, if the array is Euler, this is the relationship, a well-known relationship. So if the array is Euler, the eigenvalues, so the eigenvalue associated to the kth source is given by this expression. So so the message is the following. If we can derive an estimate of the eigenvalues of D from this relationship, we can derive an estimate of the direction arrival. Because from the phase of the eigenvalue, we get minus 2 pi fc d over c sine of theta k, and then we invert this relationship by calculating the arc sine, and we get an estimate of the direction arrival. So we have understood that given the geometry of the subarray, we know the relationship between these eigenvalues and the direction arrival. So the problem becomes the problem of estimating the eigenvalues of D. Okay, let's try to understand how to estimate the eigenvalues of D. Remember this relationship. So this is the classical expression of the data covariance matrix if the noise is ugly and white. If there are no coherent sources, the rank of this matrix is equal to the number of sources. These are the eigenvalues. We calculate the eigenvalue eigenvector decomposition, so the spectral decomposition of this matrix, we factorize, we organize the eigenvectors in the usual way. So S is an M by K matrix that is a normal base for the signal subspace. G is an M by M minus K matrix, and it is a normal base for the noise subspace, and it uses an estimate of G, remember. As you will see, Esprit uses S. Now, S and A of theta generate the same subspace, what is called the signal subspace that has dimension K. So the range of S is equal to the range of A. So it means that it should be possible to obtain the matrix S from a matrix A by post-multiplying A by a full rank matrix C. So the fact that S and A calculated in the true directional arrival, they have the same range. So they generate the same subspace. And so it must exist a full rank matrix C such that this relationship is satisfied. Now, if you now partition S exactly in the same way as we have partition A to derive the two steering matrix of the subarrays. So if you do the same partition, this relationship should be satisfied for both K. So in other words, if this is true, if you do this partition, if you multiply S by this, you multiply A by this. So you can imagine you multiply by here and here. So this quantity here is A1 and this is S1. So the relationship becomes S1 equal A1C. And the same is true for S2. So if you multiply by these both terms, you get this for K equal 2. So we have this relationship that is true both for K equal to 1 and K equal to 2, or some C that we don't know now, but we don't need to find it. The other relationship that we found was this one, the relationship between the steering matrix of the two subarrays. Now, if you derive A2 from here, A2 is S2 multiplied by the inverse of C. S2 multiplied by the inverse of C is A2. And then in place of A1, you write S1, C2 minus 1. And then you multiply by D. So if this is true and this is true, this is also true. Now, if you multiply on the right by C, you get that the relation becomes this one. Now, if you call this matrix Psi, so Psi is this matrix here, the relationship is S2 equal S1 Psi. Now, another property of matrices is the following. If you take D and you multiply on the right by C and on the left by the inverse of C, you don't change the eigenvalues. The eigenvalues of Psi and D are the same. So now remember, we understood that if we can estimate the eigenvalues of D, we can find an estimate of the directional arrival. Now we prove that the eigenvalues of D are the same as the eigenvalue of C. So the problem becomes estimate the eigenvalue of C. So how to solve this problem? So the first step is calculate the sample covariance matrix. Calculate the eigenvalue, eigenvector decomposition. Then extract S, so an estimate of S. So Esprit uses an estimate of S, not an estimate of G. Once you have an estimate of S, you partition S in the same way as you partition A to create the two subarrays. Then we have to find psi in such a way S2 is equal to S1 psi. Now, because this is an overdetermined linear system equation, so the number of unknowns is not equal to the number of equation, we can solve. So we are not able to find psi in such a way S2 is equal to S1 psi. What we do, we apply the linear least square method. So we search for psi that minimizes the distance. And so we solve this linear least square problem. And the solution is well known in closed form because it is given by the pseudo-inverse of S1. So the Moore-Penrose pseudo-inverse of S1 that multiplies S2. So if you write explicitly, this is the solution. So once you have an estimate of psi, you find the k eigenvalues. Psi is a k by k matrix. So you find the k eigenvalues, and from the phase of the eigenvalues, by inverting this relationship, you find an estimate of the k directional arrival. So this is how Esprit works. So based on the derivation, we can understand a number of properties. Esprit requires a special structure of the array, but is more general than EULA. So it does not need to be EULA. It can be EULA, but it can be anything provided it has a structure that that allow us to divide into identical subarrays, possibly with some overlap. It's much more computationally efficient than music because we don't need to make a search and find the peaks in a function. There is no risk of subspace warp. So the presence of subspace warp creates catastrophic error in the estimate of the DOA, and these are called spurious DOA estimates. So there is no risk of subspace warp. Actually, the two subarrays do not need to be calibrated. They need to be identical. Like music, because it relies on a property of the matrix RS to be full rank. So like music, also Esprit can be used if there are highly correlated sources. So it does not work anymore. If the array is EULA, it's very easy to create the two subarrays, and what we typically do is to consider the first m-1 sensor as the first subarray and the last m-1 the second subarray with an overlap of m-2 elements. This is the classical Esprit, and the solution of Esprit is found by solving a least square problem. The performance can be slightly improved if instead of using the least square method, you use the total least square method. I'm not entering the detail. If you are curious, you can check. So there is a version of Esprit called TLS Esprit, where the step 2, so the calculation of the linear least square solution, is replaced by the total least square solution, which is, I mean, the computational complexity is higher, but you can achieve better performance. And if you are familiar with other methods, I mean, Esprit, the method it works is closely somehow related to other methods proposed before Esprit, like the state space Toeplitz approximation method, TAM, or the matrix pencil beamformer proposed by Hua and Sarkar. And as I said, this method, from the computational point of view, should be preferred to music because it's a search-free approach, in the sense we don't need to make a nonlinear search with respect to a parameter to find the maximum. So from computational complexity, Esprit is better than music. In terms of estimation accuracy, root music has slightly better performance than Esprit, and we will see this by numerical simulation. So even if root music has performance that are slightly better than Esprit, root music can be used only for Euler array. And the computational complexity of root music is higher than Esprit. So for this reason, Esprit and modification of Esprit are probably the most popular subspace method for directional arrival estimation. Okay, this is another numerical example. So I illustrate this, and then I think you can try to run the MATLAB code and rederive these results, change the parameter, and so on. So the assumptions are the same as before. Again, we assume that there are three sources, a triangle, 10 degrees, 16 degrees, 45 degrees. And the power is different. So the second source has double the power of the first and third. This matrix is diagonal, so the sources are uncorrelated. So both music and Esprit, but also Capon, can work in this case. The distance between the two closest sources satisfies the Rayleigh limit, and this is what you get. So so first of all, I don't report here Esprit because Esprit does not have a spectrum that you can plot. Esprit provides directly the estimate of the directional arrival. So you will see Esprit in a moment. So in this picture, again, I compare classical beamformer, Capon, and music. And as you can see, in this case, music and Capon can separate the two closed sources. The classical beamformer cannot separate. Why? Even if the distance is greater than the Rayleigh limit, the problem is that the sources does not have the same power. And so the peak of the weak source, the one at 10 degrees, is partially masked by the side lobe of the second strongest source. So this is why even if we are above the Rayleigh limit, the classical beamformer is not able to separate the sources. The reason is the masking effect. Capon and music that have better resolution in this scenario can still separate the two sources. Then if you apply root music and Esprit, you get an estimate of the three sources, and as you can see, both methods are able to separate all the three sources. So also Esprit is a super resolution method. So the resolution of Esprit is very similar to the resolution of root music. And I mean, there is no significant difference in the estimation accuracy. If you decrease the distance, so here it was 10, 16, 45. Now we have 12, 16, 45. Now in this case, not only Capon, not only the classical beamforming, but not even Capon is able to separate the first two sources. So at some point, after the classical beamformer, but at some point, even Capon breaks down. It's no more able to resolve the two sources. So the Capon resolution capability is intermediate between the classical beamforming and the music method. Music can still separate the two, and if you use root music and Esprit, both of them can separate the sources and provide a pretty good estimate of the three sources, because you have an estimate close to 12, the other close to 16, the other close to 45. Here you have an estimate close to 12, close to 16, close to 45. So Esprit and music are super resolution methods because they have a resolution that is better both of the classical beamformer and then Capon. Let's analyze the estimation accuracy now. So there are MATLAB codes to derive the bias. So how do we measure the estimation accuracy? We measure the bias of the estimate, so the mean value of the estimation error and the mean square error. At the beginning, we assume that there is only one source. So if there is only one source, there is no problem of resolution. And in fact, you can see that in this case, all the method works pretty well. So after 100 samples, 100 snapshots, the bias is negligible for all the four methods. Then, if you calculate the mean square error and you compare with the Cramer-Rao bound, you can see that the classical beamforming is asymptotically efficient. Actually, it is the one who works better. Why? Because in this scenario, if the additive noise is white and Gaussian, actually the classical beamformer is the maximum likely. And the maximum likely is the best possible. So that's why, in terms of estimation accuracy, the classical beamformer is the best one. but only because the noise is additive and wide, and there is only one source, so there are no resolution problems. Then we have Capon and then root music. All of them are asymptotically efficient because the mean square error tends to the Cranrao bound. Esprit, as I said, has performance that are slightly worse than root music. If we increase the number of sensors, obviously things gets better. So the bias start to be negligible for a smaller number of snapshots for all of them. The mean square error is smaller. The classical beamformer is efficient, and so on. Obviously, if you increase M, the performance gets better, no doubt. Now, let's assume that there are two sources spaced by 4 degrees. In this case, the classical beamformer and Capon are not able to separate the sources. So they cannot be used in this case. So they breaks down, they don't work. So let's compare the performance in this scenario by using these two super resolution methods, root music and Esprit. The sources, so there are two sources with different power. So you should notice that the power is different. The second source has double the power of the first source. So I expect that the second source, because it has more power, it will be estimated better. The bias is negligible after 30 snapshots. So 30 snapshots are enough to have an unbiased estimate. So the bias, forget. And these are the two Cranrao bounds. And then we have the mean square error of root music. And as you can see, root music is asymptotically efficient. The two Cranrao bounds are slightly different. Why? For the reason I told you before. Because the power of the second source is larger. And so the Cranrao bound is smaller, is lower, because we can achieve better estimation accuracy. So root music is asymptotically efficient, like the maximum likelihood method, but it has computational complexity much, much smaller than the maximum likelihood. I'm talking about both the deterministic maximum likelihood and the stochastic maximum likelihood. So in other words, root music achieved the same performance asymptotically of the maximum likelihood with much less computational complexity. And it can resolve closed sources that cannot be separated by using neither the classical beamformer nor Capon. Esprit has estimation accuracy that is slightly worse than root music, but root music, remember, can be used only if the array is Euler, and the computational complexity of root music is definitely higher than Esprit. So, I mean, the choice between the two is not obvious. It depends on the particular application. It's important that you understand the different pros and cons of every method so that for your problem, you can decide what is the best method. Because there is no method that are always the best from any point of view. So it depends on the constraint that you have. So sometimes the best choice could be Esprit, sometimes root music, sometimes Capon, sometimes the classical beamformer. So these are another numerical example. Okay, this plot, sorry. this plot was as a function of the number of snapshots. Now I fix the number of snapshots, 128, and I plot the bias and the mean-square error as a function of the signal-to-noise ratio. So what changes when you move is the power of the noise. So the power of the second source is always 2. The power of the first source is always 1. If you change the power of the noise, you change both the signal-to-noise ratio for source 1 and source 2. So what I plot here is the signal-to-noise ratio of source 1. And you can see both the methods are asymptotically unbiased when the signal-to-noise ratio increases. Root music is efficient, and Esprit has a small loss with respect to root music, as we know. But it's also consistent because the mean-square error tends to 0 when either n or the signal-to-noise ratio increases. So both the methods are consistent. But root music is more efficient than Esprit. There is another method that is described in the view graph, but I will skip this because we don't have time. So if you want, you can read it. And this method has performance intermediate. So it has good performance, good computational complexity. So it has some advantages, but this is called spatial Uli-Walker, but I have no time to enter in the details. So what I want to, I want to close this chapter by telling you how to estimate K, because when you calculate the estimate of the directional arrival by using Esprit or music, you have to fix K, you have to choose K. So to choose K, you can use a model order selection method, Akai K, minimum description length. I mean, there are methods. I didn't describe them in detail. And another option is the following. So I want to show one way to estimate K. So remember, when we assume that the signal is deterministic, we derive the least square estimate of the signal, and the least square estimate was the pseudo-inverse of A times Y. So you can write in this way. So once we have an estimate of the directional arrival, we can reconstruct the K signals in this way. Now, if you tell music and Esprit that K is 5, they give you back 5 estimates. How can we decide if all the 5 corresponds to a real signal source? The idea is the following. We estimate, because especially in a passive scenario, we don't know the signal generated by the source. We don't know the shape. So what we can do is to estimate the power. So for each K, we estimate the power, and we compare to a threshold. And this threshold somehow should depend on the noise power. So if the power of the source is greater than a given value, we decide that that source is present in the environment. If it is below, we decide that from that direction, there is only noise. So this is the idea. So how should we estimate the power? the power, once we have reconstructed the signal, if you sum over time all the values of the sample modulo square, you get an estimate of the energy. And if you want the power, you can divide by n, by the number of samples. So actually, this constant 1 over n is irrelevant. So you can compare with the threshold either the energy or the power. And that's why this detector, this detection algorithm, so compare the estimated energy with the threshold, is typically called energy detector. So if you know the shape of the signal, typically we implement a meshed filter. If we don't know the shape because the signal has been generated by a source, an independent source, what we can do is estimate the energy or the power. And this is called energy detector. Actually, this detector can be proved to be the optimal non-Pearson detector to detect the presence of white Gaussian signal in additive white Gaussian noise. So, I mean, if you are familiar with the radar nomenclature, the energy detector is the optimal detector to detect a swirling 2 target in the presence of white Gaussian noise. The meshed filter is the optimal detector to detect a swirling 1 target in additive white Gaussian noise. So the idea is the following. Once we have reconstructed the K signal in this way, because once we have an estimate of the directional arrival, we can calculate the pseudo-inverse of A, and we can reconstruct the signals. From the signals, we implement the energy detector. So we estimate the capital K energies or capital K powers, and we compare with the threshold. Actually, I mean, with the aim to implement this in MATLAB, if the pseudo-inverse of A is a K by M matrix, so this is a K by M matrix. So if you call R1 the first row, R2 the second row, and so on, actually you can express this quantity as Rk y of m, modulo square. The modulo square can be written in this way. So with the Hermitian, then you calculate the Hermitian, the summation with respect to n. So you can bring Rk outside the summation. And so what you get is that this Rk, what remains in the brackets is the sample covariance matrix, and then you have Rk Hermitian. So you can express pk in this way. So again, you can express pk as a function of the sample covariance matrix that we have estimated to derive an estimate of the directional arrival. Then, if you put all these things together, you can express the vector, the k-dimensional vector of the p power estimates as the element on the main diagonal of this matrix. The pseudo-inverse of A, Ry hat, the Hermitian of the pseudo-inverse of A. So this is a very compact form that in MATLAB you can implement in one line to obtain the vector of the estimates of the k powers. So if you do this, for example, this was the previous example. So if you tell to music and Esprit, so root music and Esprit, that k is equal to 3, they derive the 3 estimates of the 3 directional arrival. And for example, if you decide to use root music, Then you estimate the power in the way that I just showed, and the power are, I mean, the estimate is pretty good. Remember, the first source are power 1, the second power 2, the third power 1. Now, what happens if you tell music or Esprit that there are 5 sources? Brute music comes back with 5 angles, and to decide if there are 5 sources or not, you can estimate the 5 powers. You get this, and you put a threshold, and clearly these two, the first one and the fourth one, are below the threshold. You throw them away, and you can conclude that there are 3 sources in the data, and these 3 sources have angle of arrival 10 point something, 15.98, so 16, and 45.1, and with powers 1.2, 2.4, 1.2. Obviously, there is an error in the estimate, but even if you start with an overestimate of the number of sources, in this way, by implementing an energy detector, you can throw away the spurious, that's called the false sources, and you can come up with an estimate of the 3 directional arrival and the 3 powers. Then you can also estimate the power of the noise in the way, you know, I mean, I already told you, from the noise eigenvalues. And this is an example obtained by applying the classical beamforming, cable beamforming, and music to some real data underwater provided by the Swedish Defense Agency. And we assume that there are 3 sources, and this is what you get. Obviously, the classical beamforming does not require a pre-estimate of the number of sources, and the same for Capon. Then, if you tell Brute Music to estimate 3 directional arrival, it provides 3 estimates. Then you estimate the power, you compare the power with the threshold. The second one is an order of magnitude smaller, so you assume, so you reject this, you decide that this is only noise. And so finally, you can say that in this data, there are 2 sources with these 2 power, 0.7, 0.2, and directional arrival minus 36.7 degrees and 58.6 degrees. So this is the way you can estimate K. So you can start from the maximum K that you expect, and then once you have estimated the directional arrival, you can estimate the power of the sources, and you can eliminate the sources. I mean, you can eliminate the directional arrival from which only the noise is coming. So this table summarizes a bit the property of the different methods. Actually, I should have added also Capon. And they are compared in terms of computational complexity, estimation accuracy and resolution, and the risk for false DOI estimated. And as I said, basically the recommendation is that if you don't have strong requirement in terms of resolution, you can use the classical beamformer, so which is the equivalent of the Bartlett polynomial. If you need higher resolution, you can use Capon, that is not reported in this table. but if you need super resolution, you can use root music or Esprit, depending on the constraint, depending on the geometry of the array, depending on the computational complexity that you can afford. Root music has better estimation accuracy, but can be used only for Euler array. Esprit requires this special property of the array, but is more general than a Euler. The computational complexity is smaller than root music. The estimation accuracy is slightly worse than root music. So I think the rest of the time, the last 20 minutes, you can use the MATLAB code and try to, to rederive this result, and you can change some parameters, and discover additional things. So for example, this MATLAB code classical Capon music beamforming compare the three methods. Let's see. So actually, the comments that I reported should be enough to understand what the code is doing. But if you run it, you can understand which figures it generates. So for example, this is the comparison when correlated sources. And the fact that they are correlated, you find from the definition of the matrix RS here, and so on. Everything is commented. So yeah, you can read and use it. So I think you can spend the next 20 minutes working on this, and if you have question, you can ask, obviously. I will be here.